So you cannot get it into 256 order. But when you have a quantum computer, if you've heard about Shor's algorithm can factor a number in O log cube of n. So in this case, if n is of the order 2 to the power 256, that becomes O of 256 cubed. That can be easily done in seconds. And so the main motivation behind using lattice-based cryptography, and lattice-based cryptography is a very recent field. It has come into existence in the last decade or so. And in fact, it's one of the most booming fields in cryptography right now, because it's what people term as post-quantum cryptography. And the main reason is that so far, quantum computers are not able to break hard lattice problems. So in the original paradigm of cryptography, where you have a large number which needs to be factored, and basically if you can factor this large number, you have broken all of cryptography. And there are existing quantum algorithms that can do that. So the next time Google goes ahead and creates a new quantum computer that can actually work on large inputs, you have broken most of RSA, you have broken most of standard cryptography, you have broken most of HTTPS, you've broken everything. And that is why mathematicians and theoretical computer scientists have gone into lattice-based cryptography, because there is so far, as of now, no quantum algorithm that can break some hard problems in lattices. So far is the key thing. I mean, if tomorrow someone comes up and breaks it up, then we'll have to go back and look at some other paradigm. But so far, it's not possible, at least so far, to break cryptography that is based on lattices. And that is the main motivation behind this talk. So I'll talk about what lattices are. So if you have studied from your chemistry times, lattices like when you have molecules, solid state chemistry, we've heard in chapter in class 12. So you have these points in a space. So, and motivated by that, lattice is a mathematical object, and we can do lots of cool things with it. So we'll go about that. So, and obviously, so this talk was intended for someone who has a decent idea about theoretical cryptography. So we'll be using terms from it. So I'll try to explain things as we go ahead. It may take some time because again, this talk comes after a semester worth of course. And if you're interested, the course is CS 406. You can, if you want, you can take it up if you're from CS or from, but this is a very great course because it's one of the most mathematical courses out there in the CS department, and it relies on something that that is very essential for the future because cryptography is everywhere. Anyways, so let's going ahead. Let's talk about what lattices are. So section 1, introduction to lattices. So simply put, a lattice is a set of points. So we have a vector space. So these are our basis of the vector space. So V1, V2, Vn is a basis of the vector space. And let's say the vector space is Rn. And so if you allow AIs to be real numbers, then the lattice would be equal, this set would be equal to the entire vector space, right? But the difference here is that AIs here are elements of Z. So this is a discrete subgroup of the layers of the vector space. So let's go ahead. So the vectors V1 to Vn are called the basis, and the matrix B is called the basis matrix. So as an example, so if these are the bases, so if you take R2, so normally these vectors would be able to span the entire Euclidean space. But because we are limiting them to be integers, you get these points, right? So this is, let's say, V2. So if in this case, the coefficient of V2 is 1 and the coefficient of V1 is 0. In this case, V2 is 2, V2 is 3, and so on, right? And so when you keep on doing this, you get this space, all right? So this is a lattice. And as you would remember from chemistry, it's very similar to what we would have studied, that you would have atoms at these points. So again, mathematically speaking, a lattice is a discrete additive subgroup of a larger group. All right, let's go ahead. Okay, so again, this, right? So let's not talk about that for now. Okay, so again, so let's take another example. So this is one. So again, if you look at this, so these are two. I'm getting some kind of beep. Is everything okay? There's a chat box, right? I have no idea. Rohini, can you answer this? Probably I don't know.
That's probably because of Zoom, brother. I guess you can continue.
No, there's a chat. There's a question in the chat. Is Shaurya coming afterwards? I'm not sure if he'll be there, but let's see. Right. Okay. You can drop your question in the chat, and please let me know if I'm going too fast, because the last time I gave this talk, it was with the professor. So in case if you have any questions, I guess so far it should be clear. Okay. What do I do with this? Right. Okay. So so let's see. So suppose you have these two lattices, and I'll just talk about why lattices are interesting for cryptography. So you can see that they are the same set of points, right? But if you would look at the vectors generating these two bases, they're different, right? So in here, this is one vector in the basis. This is another vector in the basis, right? And here, these are the vectors. So basically, it's possible to have two bases generate the same lattice. And this is actually very important for cryptography. If you have some idea about public key cryptography, I'll just give you a basic, right? Okay. So in general, when you do public key cryptography, basically, there are two keys. So by a key, I mean it's some bit string that allows you to encode messages, right? So suppose you and me are talking, and I want to send you a message. So you will send me your public key. A public key is a big bit string, and I apply some mathematical function on it, and I get an encrypted text. Now the key point here is that the public key is known to everybody, okay? But there's a private key that only you know. And to decrypt that message, you need the private key. So the public key everybody has access to. So if I encrypt some message, let's say hello to you, and I encrypt it using a public key, and I send that message out on the internet, a person can only decrypt that message if he knows your private key. The interesting part here is that you can encode the public key and the private key in the lattice. And I'll tell you why. So let's see, first of all, so the main thing to understand is that there can be two bases to generate the same lattice. So there are some bases that are good, and there are some bases that are bad. A bad basis is your public key, and a good basis is your private key. Now, the main point here is that you can do some operations quite easily with a good key, with a good basis, but some operations are very difficult to do with a bad basis. So if you have a bad basis with you as your public key, the decryption operation cannot be done with it because it'll take exponential time. But with a good basis, you can do it in polynomial time. And that is where cryptography can be used. Okay. So again, so just to recap, there can be two bases. Okay. And an equivalent basis is basically, so the condition for two bases to be equivalent is that it should be U into another basis matrix, and U must be unimodular. That means the entries must be integers and the determinant must be plus or minus 1. So again, okay, so again, let's not look at this. So one of the hard problems regarding lattices that is difficult to solve and has not been broken by quantum computer is to find a short vector in a lattice. So what do I mean by a short vector? So if you look at this vector, is this lattice, a short vector would be this, right? This is very short, right? So you start from here, this is very short. But if you look at this, it could be possible, let me just give you an example, that the shortest vector could be a linear combination. So for instance, if you take these two, if you take this and this as a basis, the shortest vector is this guy. And this will be formed by some linear combination of these two, right? But it's not this nor this. So to find the shortest vector in a basis which has only these two vectors, it takes exponential time. And it's not possible to solve it quickly. So given any arbitrary basis for a lattice, to find the shortest vector, this has not been broken by quantum computers, and we will be using this to build cryptography. Is everything clear so far? If you have questions, just let me know.
I have a question. So, like you mentioned that you define like a bad basis and a good basis based on the amount of time it would take to decrypt a message, right?
Yeah.
For like a key present in it. So, could you elaborate more on that? Because like there would be like a class, I assume, right? There's a direct class of basis, and also you later mentioned equivalent. So there would be like
no, right. Yeah. So I'll talk about it later. But the basic idea is if you have a very uniform basis, let's say something that is orthonormal in some sense, and I mean you could use gram split basis to orthonormalize this, but the problem is those vectors again. Okay, there's someone.
that's the joining in and sounds.
Oh, right. Sorry. I thought that someone typed some message. Okay, that's a join message, right? Sorry, it's been a while since I used to. Okay, right. So your question is that, yeah. So, so I would not say class as such. I mean, so basically, in general, given any arbitrary basis or random basis, so what your question should be more appropriate is what is a good basis, right? So the general problem of having a bad basis to solve, it's intractable. But the basic idea is, as I'll prove later on, there's an approximation algorithm to find the shortest or the closest vector to a particular lattice point. And when you have a basis that is very even, in the sense it's almost orthonormal, it turns out that it's it gives a good solution with a very high probability. And in cryptography, what we are really caring about is probability, right? So essentially, if you have a good basis, something like this, you can basically solve these approximation problems with a very high accuracy, and that works out mostly for cryptography. The reason why you cannot orthogonalize this in Gram-Schmidt is that the resulting vector sets may not generate the same basis, the same lattice. So again, there's a mathematical proof for that. I can share that with you, but the basic idea from an overview is that, you know, you can approximate, like let's say you can approximate the closest point, right? Or you can approximate the shortest vector. And another hard problem for cryptography is finding the closest point. So let's say I'm given a random point, let's say here, and the problem is to find the shortest latest point. So there is an approximation algorithm for that. And we can think about one approximation algorithm for that. The fundamental point being is that if that basis is well structured, then you can basically easily get to the original point. But if it's something like this, it's not possible. I'll come to it later on. Class-wise, there should be some class distinction, but from what I studied, I didn't find any. I'll go ahead and answer you later. Is that okay? So there.
Yeah. Okay. Fair enough. Yeah.
Sure. So okay. So the next part, again, we just want to give a bound on the smallest vector point. I'll skip it for now. It's a bit complicated. Okay. So basically, what this does is that lambda1 is basically the shortest vector in this lattice, and so this is the length of the shortest vector, and basically shows that you can bound it. Again, I'm leaving this for now. It's a simple proof. I'll come back to it later if required. So let's just go about what are hard problems in a lattice. So shortest vector. Sorry.
You said something was bound.
Yeah. So I said it's very difficult to find small vectors in a lattice, right?
Okay.
Right, but you can actually bound it, and it turns out to be an exponential kind of thing because it has a determinant with a.
So you by a vector you fine.
Yeah, sorry, go ahead.
So you lattice is a collection of. Okay, fine. It's a subset of Rn, right? Basically.
Yeah, it's a subset of Rn where the linear coefficients are integers. Okay, so it's kind of like you can only go in integer steps. You cannot go into.
So shortest vector means one with the minimum.
So as I showed you,
distance from zero.
No, I mean this is a vector space, right? You can say from zero, obviously, but it's a vector space. So you generate some vectors, right? I mean there are two interpretations for vectors, right? You can just add them up, and you get some vector. You can take its Euclidean norm, and if you center everything at zero, then it's a distance from zero, obviously. Yes.
Right. Yeah. Okay.
So in this case, it's the shortest vector. This or this.
So it will be zero, right? I mean, zero will obviously be there.
That's a trivial solution. We're not talking about it. Yeah.
Okay, and if it's not zero, then one will be there, right? 1 0 0 0. That vector will be there, right?
No. See, suppose this is the basis. You see these two vectors, v1, v2.
Okay.
Suppose this is the basis. So this basis can generate this entire lattice. Is this the shortest vector?
Right.
This is the shortest vector.
Yeah.
Right. So again, if you have a good basis, then this is trivially this. But if you don't have a good basis, it's not that. Does that make sense?
Yeah, it does.
Can you please elaborate on good and bad basis once more? And what did you say about class? I didn't get that.
So again, let's just think a good basis is a very even basis. So this is a very even basis in the sense it's very orthonormal. Does that make sense?
No, I got that, but not exactly. But like you said that we are defining it to be a good basis. So like V1 and V2.
Again, there is no precise mathematical. So when you come into the numerical approximations later on, you can define the error when you do cryptography. So if you studied some amount of theoretical cryptography, there is no 100% guarantee in anything. Okay. So when you're talking about decryption, when you go into the theoretical side, it's always a probability. It's always a probability distribution. So by a good basis, I mean something that has a very high probability. And by a bad basis, I mean something that has a very low probability. So in this case, let's say your approximation solution to the shortest vector is just V1, or let's say min of V1, V2, Vn, right? So in this case, the probability is going to be zero. Whereas in this case,
we are talking about the shortest vector that we can get in terms of the basis that we are taking.
It's not exactly the shortest vector. There are a lot of problems out there. So a good basis is something that is very even and orthonormal. And this results in exact solutions to otherwise hard problems. So that is the not a definition exactly. I think there is some definition mathematically. Let me just check it for you.
You had mentioned something regarding the probability, right, of getting it good. So like there's probably
See,
one can set
as
up
I
a
said,
cutoff.
yeah,
Right.
as I said, a good basis is a set of almost orthonormal vectors with small norms. Again, if you talk about a theoretical definition, I'm not
So
sure
we
if
try to fit the best bases to get them almost orthogonal, right?
the problem is it's not possible to get this orthonormal basis from a bad set. So when you are generating a basis, so when you're generating a lattice, you have the freedom of choosing these vectors, right? So let's say I choose some orthonormal vectors as my private key, and then I generate some linear combination out of it, and then I send it out as the public public key. I can do that, but the reverse is not possible. At least it's not been proven, but it's a heuristic assumption that it's not possible. Again, if you go into cryptography, there are some assumptions out there that do not have proofs. So as someone who's into math, this may seem a bit counterintuitive. Like when you do cryptography in RSA, if I don't know if you know about RSA, there's an assumption that's very difficult to factor hard times or large times. There's an assumption, implicit assumption, and you base entire cryptography on that. But there is no proof. You do not know that P is equal to NP, right? So there is no proof for that, but you go with that assumption. So here the assumption is that in these bases, which are not orthonormal, it's very difficult to do these problems. And this is the latest assumption. And lattice-based cryptography is built on the assumption that there probably is not some supercomputer or some quantum computer out there that can break this algorithm. And we go and build our entire cryptography on this. So there is no mathematical basis to it. So these are assumptions. So I know this is a bit difficult, and that I think differs like from what mathematicians would like and what computer scientists like. But in computer science, there are a lot of assumptions that we go ahead with, and this is one of them. So again, mathematically speaking, at least from what I know, I don't think there's a proper definition as such. But it is what it is. Does that answer your question to some extent?
Yeah.
Again, I'm not a very big expert at this. I just took it as a project. I studied it for 2 months, and this is a very recent research topic, and the papers are very complicated in some sense. So again, and because this was at a very short notice, I couldn't prepare much. So yeah, I just tried to give as much as I could understand, and there could be some holes in it. So again, I'm just letting you know about that.
Okay, no problem. Thank you.
Because I'm no expert at this. I'm a second year student, right? And this is like people are doing PhDs on this. So yeah, it's short. Okay. Again, this is not important. We're bounding. So okay, again, what are hard problems? So find a vector in the lattice. So what is lambda 1? So lambda 1 is the shortest length. So again, this is the length of the shortest vector. Let's just look at that as lambda 1. So the shortest vector problem says that you have to find a vector in the lattice whose length is less than or equal to gamma into lambda 1. Let's say gamma is 2. So you have to find a vector that is at most 2 times the smallest vector length. And gamma can be any parameter. And again, there is no efficient algorithm for this. So let gamma be any polynomial term. It's not possible. So if it's 100, 1000, doesn't matter. There is no efficient algorithm for this for a general basis. Similarly, shortest independent pair vector. So what is lambda n? So again, I should have defined this. Okay, let's just go through it once again. So lambda k denotes the smallest radius of a ball containing k linearly independent vectors. So okay, so essentially, if you look at this, this is one vector. This is another vector. Let's suppose that the second basis was not this, but this. Okay, right? Suppose it was this. Then the second smallest vector would be this, right? But that's trivial because if I know the first smallest vector, I can easily know this. That is not lambda 2. The length of this is lambda 1. The length of lambda 2 will be this, if this was the basis vector. So basically, you take linearly independent vectors and you find the k smallest of them. So lambda k, the smallest radius of a ball containing a. So it's the length of the largest vector. So if you take k linearly independent vectors that are the smallest, and you take the length of the largest one of them, that is lambda k. So essentially, it's a ball which contains k linearly independent vectors. So in this case, this ball would be this. If you go like this, if this was the basis vector. Okay?
But even in that, can you go to that picture? So even
Yes.
this this picture. So v1 dash and v2 dash, the original ones.
Yeah.
So our new basis was some.
No, I said this
v2
was
dash.
if this was the basis vector. This.
Yeah, but still v1 dash and v2 dash form a linearly independent set, right? So
but this point won't be in the basis then, right? Because if I have this and this as my basis, then I'll get this set and I'll get this and I'll get and this will repeat, right? So you won't be able to find this point. The lattice will become a sub-lattice in that case. Does that make sense?
Yes.
Okay. Yeah. Okay, so again, now here, instead of finding one vector, you have to find n vectors, right? Whose length is less than, again, the value of this should be at most gamma times lambda n. So basically the length of the largest vector will be at most gamma times lambda n. This is also not possible to solve efficiently. Similarly, the other important problem is a closest vector problem. So, right. So again, now you're given a random v in the Euclidean space. It does not have to be a lattice point. And you have to, so there will be a closest lattice point to it, right? Because people are leaving. Okay, fine. So for instance, if I take this point, the closest would be this, right? So you have to find a lattice element, which is, so there will be a closest vector. You cannot estimate it easily, but if you can find one of them, one lattice point, which is at most gamma times farther than the closest lattice point, then you're done. So you don't have to necessarily give you the closest, but something else is a good approximation to it. So here gamma could be, gamma, if gamma is 1, then it has to be the exact closest vector. But if it's something else, then it's okay, you can give an approximation. Similarly, BDD. Now here the difference is you're given a close point to a lattice element. So here you are at an arbitrary point. So here you have a close point. Let's say this. Then you have to give me exactly this. That's BDD, and even that is difficult to solve. Again, these are assumptions. I mean, nobody knows a p time algorithm for this. And so the assumption is that these cannot be, and there is no quantum polynomial time algorithm yet.
Can you just tell what is BDD once more?
You're given, these are lattice points, right?
Yes.
So I give you a very close point. Let's say I give you this point.
Which is not in the lattice.
Yeah, not in the lattice. You have to give me back this. This may seem trivial to you if you look at it this way, but given a very random basis, it's not possible. I'll show you later on why that's the case. Okay. Let's just show you. I think there's a picture here. 1 second. There was a picture. Sorry. I think it's in the second half. We'll not talk about it so much. It's going to get. See. Let's take this. Let's take this. Right. So okay. In fact, okay. Let's skip it for now. Sorry. We'll have to talk about Babai's algorithm for that. Let's leave it for now. Okay. Sorry. Yeah. Because I will come to why that is difficult. Okay. So next, coming to short integer solutions. So it's a problem in a lattice. So this may seem not related to a lattice, but it's actually generates into a lattice problem. So let's talk about what this problem is. It's a mathematical problem. So you're given m vectors, each with n elements, and every element in this vector is from the field ZQ. So you have to find a solution to the following equation: a1 z1 plus a2 z2 up to am zm equal to 0, and 0 is the null vector, and the operations are carried out in this field. So I'm assuming you're comfortable with basic field theory, and and zi's have to be -1, 0, or 1. Okay. So in some sense zi's are limited to this set. Is this equation clear? It's simple. You can solve it into it will become a matrix if you solve it out. But the operations are in the modular field, modular prime Q. Okay. Right. I can leave this for now. So okay. So what does it have to do with the lattice? So let's first convert this into a matrix form. So this will be equal to AZ equal to 0, where the entities of Z are Zi, and the columns of A are Ais. So you want AZ equal to 0 mod Q. Now let's see. Does this form a lattice? So if I constrain Z to have only integer entries, does this form a lattice? It will, right? Because you take any linear combination with integer entries, it's going to satisfy this equation, right? So alpha A into alpha Z1 plus beta Z2, where alpha beta are integers, will satisfy this, right? So the cellular solutions of this Z, where Z are integers, is a lattice. Okay. Now let's not. So this is the latest. So the solution set of this is the latest. But in our original problem, we required Zi to be in -1, 0, 1. So if you think about the L infinity norm of Z, the L infinity norm of the solution must be less than equal to 1, right? So if you use the L infinity norm as your metric for a shortness, then the solution of this problem must be a short vector in this lattice. It has to be a short vector. So essentially, asking to solve this means that you're able to find a short vector in this lattice, where the norm is the L infinity norm. Again, I have mentioned, so it doesn't have to be 1. As long as it is sufficiently small than C, Q, this basically becomes hard because you have to find a sufficiently small vector in this lattice. Okay, so is this clear? People have left. Okay, I just, yeah.
What is A and what's mod Q on the side if I'm not causality?
Your voice is cutting off, sorry.
What does mod Q imply?
Mod Q module. Oh, you don't know what mod Q is. So if a number X is equal to, let's say, A into Q plus R, if you remember your Euclid division lemma. So the R is the remainder. So it's basically a modular class.
The remainder.
Yeah, I think you should have done it in if you did some
No, it's just like it came at an unexpected place.
It's not exactly a remainder. It's an element. You can represent it by the remainder. It's a bit different than that. It's a field, but okay. For now you can think of it as a remainder. Okay, it's a bit different than that essentially. If you take up group theory, you'll understand it. But okay, think of it as a remainder for now. So
what's the L infinity norm?
So if you have so if you have a vector, so L infinity norm is the largest element, the largest absolute value of an element. So suppose my vector is, let's say, -2, 4, 5, 6. The L infinity norm will be 6. It's the largest value of the largest element in that vector by modular, by the absolute value. So if it's -8, 2, L infinity norm is 8. Okay. So it's some sense of finding the length. So there can be different metrics for length, right? You can have absolute value, you can have square x square plus y square root under. So there are different norms, but this is the L infinity norm. Okay. So now this is getting, so we'll have to talk about, so do you guys have any idea what a hash function is? You must have heard about SHA-256, MD5.
I mean, heard about it, but never actually, how does it work for anything?
Is it a function that is easy to compute, but difficult to compute the inverse given the output?
That's true, that you could think of it that way. There is some more rigorous definition to it, but yes. So given when you see the output, you won't be able to guess the input. In fact, not just guess, you think the input is random. Sorry.
Yeah. Also, the inverse is not defined technically, right? Like for
so it could be defined. I mean, but you could define the inverse as you could. So if you take a generic hash function, which is SHA-256, the domain of that is infinity. So in that case, true. So I mean, it can be any arbitrary length, but you also have hash functions that have finite elements in the domain. That's what we're talking about here. So in that case, you can have the inverse as a set, right? So that works. So again, so let's define a function. Let's just define a function, HJ equal to A into Z. Okay, let's just define it, and this is, so there's a definition of what collision resistance means. So if you, okay, I'll just give you a brief idea. So remember, our inputs are 0 and 1. So the Z has either 0 or 1. And let's say given this output, you can predict an input that maps exactly to this. Suppose I evaluated at Z1. So I got this, and you could find an input Z2 such that AZ2 is equal to AZ1. This would imply A into Z1 minus Z2 is equal to 0. Right? Now, what are the entries of this vector? This is -1, 0, or 1. Right? So essentially, we can solve. So we have found a short vector which satisfies this. Right? So actually, there's. Can you think of one nuance with this, like this entire argument that, that this is difficult to find, etc., etc. So it should be difficult to compute. But there's a thing that is missing here, so our assumption was that this problem is difficult in arbitrary lattices, right? Like in a general random lattice, right? But this is a special class of lattices, right? So it could be possible that it is easy to find a short vector in this lattice. Remember, it's a special class. The assumption is for generic lattices. Not all lattices can be expressed in this form, right? But again, it can be proven that if you can break, you can find a short vector in this lattice, then you can do a construction to find a short vector in an arbitrary lattice. That exists. So that's why if you can find another input that maps to the same output, you have found a short vector in this lattice. This breaks the assumption that we cannot do that. Why we cannot do that? Because again, if we could have done this, then we have an algorithm, right? And because we so far nobody has found an algorithm. So that's why this is a collision resistant hash function that given an output, you're not able to find an input. Is that clear? So, and because hash functions are used everywhere, you can build lots of interesting cryptography from it. Like I'll just talk about it. Okay, we have not actually seen that, but okay. Again, this will get a bit. They've actually proven why this is hard. I think we should leave this. It's going to get very technical, and we don't have much time. So basically, again, this basically proves that you can break it in a generic lattice. If you can break this thing, there is some. I don't want to go into sampling from a Gaussian and stuff, because then you'll have to know what a Gaussian is. I am assuming most of you are first years. So, but the basic idea is that you have found a hash function.
First year would also know Gaussian, right? Because I think PH1 mein to karte hain, but theek hai.
Yeah. I think we do know what the Gauss is.
Wait, we learned Gaussian in first year?
Yeah, PH1 mein karte hain.
Even in
Dude, I have no memory.
Year of Gaussian is Gaussian.
I have no memory, man.
I mean, fair enough. They teach it like for like a lecture or so.
No, I really have no memory because we learned Gaussian in our CS course in first sem. So that's why we had a lot of analysis to it. So that's what I thought. And I think it's generally covered in a probability and statistics course, right?
Yeah, it's always this, yeah.
Yeah. So I mean, even when I was in first year, I didn't know what a Gaussian actually was. I knew कि Gaussian hota hai, but Q hota hai, that only I came to know in the second year. So, and that would actually rely on, again, I think you should. So the basic idea is that you can, I mean, we don't have much time. I'll skip it for now. We'll come back to it if we have some time. So again, basically we have created a hash function using lattices, and using a hash function, we can build many cryptographic tools. We cannot get public key cryptography, PK means public key, but you can get secret SKE, which is secret key cryptography or secret key encryption. So again, I can define what that means. Let's see, basically so in a public key, I give out a key, right? In a secret key, basically you and me, we meet in the real world over a cup of coffee, and I give you a key, a very big string. And then I say, when we meet on the internet, you can use this key to encrypt a message. And then I can decrypt it using the same key. So there's the same string out there, which can decrypt your messages. And assuming that nobody else knows this key, which can be randomly generated, for any other eavesdropper, any other person, any message you send will be random gibberish. That's secret key encryption. And you can use hash functions to build it. You also require something called PRF, a pseudo-random function, but it can be built from this. So let's just leave it at that. But you can basically build secret key encryption using simply this idea that I can mask. Given a lattice vector, given a matrix A, I built a hash function. Okay, right. So again, we have built cryptography, and you can actually use this, and it's actually very simple to implement if you think about it. You just need to find any which with a very bad basis. Again, what is a bad basis? Again, you have to come. We leave that for now, but it's basically something that's very random. So what you do is you generate a good basis, and then you take random linear combinations, check if the angle is very small, and also ensure that they are not linearly dependent, and then you get a very bad basis because it's not possible to find a short vector in it, at least so far, at least. Okay. Learning with errors. Let's see. Should I go through this? How much time do we have? Hello.
Yeah, so we do have it like for up to 8:30 is what we put the schedule as, but you can feel free to put as much as, I mean, till wherever you would like to end it with closure. I guess that's your discretion.
So far, The only thing that could be difficult is why it's a bad lattice, right? That part is, I guess, not completely understood. Other than that, right, I don't think we should actually go into trapdoors. This will get too complicated. Again, sorry about this, but Rohini called me just 1 minute before I showed up, so again, I didn't really structure this.
Yeah, I mean, we must say we're really thankful you showed up. Yeah, like this is honestly pretty great. Just telling that. Yeah.
Sure. I mean, always grateful to be of help. Yeah, I mean, MMPA and obviously to attend the events, and so yeah. Okay, we'll not go into this. Let's do something else. So, do you want me? Should I talk about generic cryptography? Like I've told you about what I can do that, or do you want me to just cover this? Do you want me to talk about theoretical cryptography? Whatever you guys want.
So actually, I had like one question, since you like pointed out that the main motivation of why this is made was because Shor's, and so like Shor's factoring problem was in what do you say? It was in the class which is somewhere in between NP and NP hard in terms of whatever they call it. I may be a little wrong in terminologies here. Forgive me for that. But importantly, factoring doesn't fall under NP complete, because if it fell under NP complete, then that's like dangerously strong.
Right.
So like, is this something like that? Like, does the lattice thing, have they shown any equivalence to NP complete for the problem of the shortest path, say, or yeah?
Yeah, right. I actually have a slide for that. Right. So okay, let's think of LW is another problem, which right. Okay, no, this is a bit different. So this does from SPP to LWE, and okay, this will not work. Right. So what you're trying to ask is finding a shortest vector in the lattice. Have we showed it that if we can break it, we can break some, let's say, hard problem in, let's say, some NP hard problem? Is that what your question is?
I mean, more about NP complete. Like, is there any relation between these problems to do they belong?
Oh, you mean a reduction from this to NP? Some, let's say, 3-SAT or circuit SAT.
Yeah.
I'm not sure if there is one. Let me search it up. Reduction from lattice to 3-SAT.
Also, this latest problem, so it should be a yes/no problem, right? I mean, it should be a decision problem.
So basically, about that, yeah. So you can basically convert a decision problem into a search problem. They're equivalent. I think someone showed it. Where did that go? Oh, dude, what am I doing? Where is the? What did I just? Yeah, sorry, it gets minimized. I'm new to macOS. Yeah. Right. So again, you can show an equivalence and go, and because if you can, if you in search, you can get the decision, and there's a reduction in the other way as well. So you can basically you can show that they're equivalent. I think about LW as another lattice problem, which is very similar to searching for the shortest vector. It's a bit different, but it can be formulated to something similar. Okay. So there is a reduction in both directions. This means a reduction from this to this. Okay?
Yeah.
Although why in this slide? So I took the slide from a presentation. This is very trivial, right? Search obviously implies decisions, but okay. Right. So again, where was I? Right. So there is an NP hardness and NP completeness.
No, they are saying decision. I mean, if you know how to solve decision, then you can solve search. That's what that means, right? That.
No, the direction is actually ulta. Search implies decision. You can reduce search to decision. Oh, sorry. I'm sorry. Yeah. Sorry. Yeah. Ulta kar diya maine. Basically, if you have an oracle for decision, you can get an oracle for search.
Yeah.
Right? This is the direction of the inequality. Sorry. Yeah, what was I coming to? There is a proof, but I do not know what the proof is. Where did it go? NP hardness of lattice problems. I mean, it has to be an NP. I mean, if you think about it, because we're really looking at quantum.
Yeah,
we are really considered about quantum, right? We really are worried about quantum algorithms, right?
Yeah, like, I mean, the main thing with quantum is, I mean, a bunch of people are like, you haven't still shown anything from NP complete being solved by quantum. And I think like I think I remember seeing one where the what do we say? What was that name? Like the graph problem. I forgot. The traveling salesman problem was sped up, not
Yeah,
like
right.
gotten to,
I mean, you can
yeah,
speed
but
it up
just
using
sped up.
Grover's algorithm as well, right?
Yeah, it was actually, it was using Grover's, and they offered like more than quadratic but not exponential.
Right. Yeah. Yeah. I think I've seen that somewhere. Yeah. I mean, you can obviously use Grover to. Yeah. Hello. Yeah. Go ahead.
Grover is like always
Yeah,
fail-safe
always
for
there.
quadratic.
Yeah, for anything. But okay, so they may have shown something better. Yeah, but like the main problem with like in terms of cryptography, and this is not complexity theory. Thing is, if you look at any cryptography you see these days, it's all based upon RSA. It's all based upon factoring. It's all based upon Rabin. And if you can factor a large number, which is the product of two large primes, you're done with, because that's a trapdoor to invert everything. Like what I said here, if you remember, I talked about a secret key, right? In these cases, the secret key is, so if you have n equal to pq as a public key, the secret key is simply p comma q. So if you can just break n into p and q, then you're done, right? Everything is gone, because now you have the secret key to decrypt stuff. So that is the main, reason why people work with this, because if you can somehow, because quantum wise, you can actually do that, right? You can factor it out. So that's the main reason. In terms of whether so we are not really concerned about if breaking latest problem would make p equal to np or something like that. We really want to build something, like do some encryption that cannot be broken by trivially by a quantum algorithm. That's it. Like that's the motivation. This should be something more like talking for latest in terms of, is it like complexity theory? Again, I do not know about that, but the motivation for cryptography is that. Is that okay?
Yep.
So again, they have shown some. Okay, I think if you remember CVP, closest vector point. So basically, so they're doing a reduction of subset to this. So subset is some problem if this is an NP. It's in fact NP complete, right? So I think, so in some sense, if you think about it, we're just finding some subset, and a subset can be -1, 1, right? Like it's 0 or 1, just choose or don't choose. So in some sense, that also looks like a lattice, right? A short lattice vector, in fact, if you think about it, like the way we did about SIS, right?
Right.
In some sense, I mean, just an analogous thing. Like I think they're doing something similar here. Like I think it's similar, right? LP non. Again, I'm not going into like people. I think have already started leaving a lot, but the essential idea is that okay, you can. I think like this should not be very difficult to go into. Like you can actually check it out. That if you just formulate it as a lattice again, and then find a short vector, and the short vector should be able to solve this, assuming that the short vector also has some approximation to it. I don't know. Let's see. Okay, I'll just do that now. Okay. Right. So that was one part, that like short vectors equal to hash functions equal to secret key cryptography, SKE, secret key encryption. For public key, you have this thing called LW. I think we can go through it quickly. Okay. So right. So in learning with errors, so this is another paradigm. So like we had SIS. This is another hard problem that is related to a lattice. So let's say you have a vector B. You have let's say, okay, let's go through it. Let's go through it again. Yeah. Right. So what you have is that you have it's a random matrix, actually. Sorry about this. But okay, so basically what you do is you have a matrix A, you take some S, which is a secret. So remember, in cryptography, we are concerned with about a secret, a private key. So you take that, you multiply it. You can write it as a transpose, like normally the way you do is A into S. But for some reason in the literature, they use this notation where they like to keep everything like as row vectors. So even though S is a column vector, but okay. So you do ST into A and you add some error term here. So E is a short vector. Again, shortness could be in terms of different norms. Let's talk about L infinity norm for now. Let's say the elements are between 1 to -1. So again, this is all happening in ZQN, right? And so you get this vector B. Here BT is a row vector, so B will be a column vector. So what LWE says is that when the secret is unknown, so when you do not know this, right? When you do not know this thing will look random. Why will it look random? Because you can randomly sample A, you can randomly sample E, subject to E being short. So what the assumption says, learning with errors, is that if you do not know S, this might as well be a very random vector that you generated. But if you know S, then you can show that you can distinguish between a random vector and a vector of this form. So essentially, we are given AI bi equal to S into S. This is we have multiplied it off, S into AI. So plus E. So S is again S is a vector, and S is a number. So if here, I think they have made a mistake here, but okay, let's skip this. So again, we have this. So the decision problem. So there are two problems for this. Decision problem is to distinguish. So again, so basically, I can either give you something of this form. I can give you a completely random vector B, and I ask you to distinguish. You tell me whether it's of this form or it's a random vector. And the search problem is given such a vector B. Just find me this. So if you can do the search problem, you can obviously solve the distinction problem because you can get S out. So okay, so let's do one reduction. So if I can solve SIS, I can solve LWE. This is easy to see. If you solve SIS and find, so we know what A is, right? So A is something it's like common knowledge. So it's like what you can say, if you have a standard. So when you're encrypting stuff, you have this. So let's say when you release an encryption algorithm, you know there are some constants embedded. So in this case, let's say when you're communicating, you just say, okay, this is my A, right? So A everybody knows, and then if I can find a short Z such that AZ equal to 0, then what I do is let's multiply with this, right? So then you get BTZ is equal to E transpose into Z because AZ is 0. Now think about this. Z is short, E is short, right? So if you have very, very small elements, and by the way, the value of Q is very large here. It can be like 2 to the power 128 or something like that, of that order. So because the number of elements is small, let's say N is, let's say 50 or let's say 100. So when you multiply, let's say this can be, let's say around 1000, maybe 10,000, but not more, not very large. Whereas if I take a random vector R completely and I multiply it by Z, because the numbers can be arbitrarily large, this can be very, very big, right? So essentially, probabilistically, what I do is I take the Z and multiply it by BT, and if I see it's very small, I say, okay, no, this is of this form and not a random vector, and there will be a very, very high probability that I'll be correct, and that's all that I require. So this is a probability reduction, right? And because and what you can do is you can no, you cannot do that. So basically, there is another reduction here that shows that if you can solve probabilistically, you can actually solve it with certainty. I have skipped it in the slides, but there's also a proof for that. But basically, with high probability, I'll be able to solve the LWE if I can solve SIS. And it turns out that I can actually solve it with 100% certainty. There's a reduction for that. And in the reverse side, there is a quantum reduction from SIS to LWE. Even I don't know what this is. It's a bit very complicated, so I skipped it while studying. But there is a reduction in both directions. But this is quantum in this case. Okay. So again, there are some reduction proofs. They are very recent papers, 2009, 2000. There was one paper in 2011 covered it later in the talk. So very recent stuff and interesting stuff. But again, work is going on this. So okay, let's talk about LW and BDD. People are leaving like flies. I think it's getting either too technical or I don't know. Okay, right. So what was BDD? If you remember, BDD was to find a close vector point. So if you're given a point in a lattice which is very, very close, then give me the original lattice point, right? So here, if you remember, AST, like we talked previously, is a lattice, right? Where S is constrained to be in integers, and ET is a small displacement to it, right? So this is a lattice point, and I have displaced it to give me a random point. If I can find the closest lattice point, STA, I can get the S back by doing Gaussian elimination, right? It is one candidate S, at least. Okay, so yeah, so then so I basically found the secret S if I can solve BDD. So it's a reduction in that direction as well. Again, some properties. Let's leave that. We don't have much time. So let's talk about something interesting. And so let's see how we can build public key cryptography from LWE. And I think I'll end the talk at this. So far we basically covered secret key encryption. And so in this case, you'll be very happy to know that this is very self-contained. So I can basically build public key encryption from LWE. So that will give you closure in the sense that you can basically use whatever you've seen so far, assuming that those data problems are hard, and you can go ahead and build encryption scheme that is based on public encryption. Okay, so let's go through this. It is a bit complicated. Let's see how far I've done here. Okay, we don't do GGH. So I'll also share some links with you. I can share this PDF, some resources if you're interested. I can also share, so I can do that with you. I think I'll share that with Rohini. So I guess the 13 or 14 people who are in this talk, they are really like interested in this stuff. So we can do that. And okay, so yeah. Right. So let's talk about what public key encryption is. So again, essentially the idea is that you as a person want to send some messages to, let's say, this guy, this girl, right? And she will send out her public key that everybody knows, right? So what is happening here is that this is a public key. So what's a public key again? It's a string out there that everybody knows. So let's say let's call her. Yeah. So the standard notation in cryptography is Alice and Bob, and this guy is called Eve, although he's a guy here for some reason. But generally, that's the notation you see everywhere. So Alice sends out her public key. She let's say she puts it on her website, and she says, "Key, using this, encrypt a message and tell it back to me." Okay. So what we'll show here is that we'll encrypt a bit. Okay. So if you can encrypt a bit, we can encrypt anything, right? Because if I so Alice Bob will send something here, and with high probability, Eve will be able to get that as 0 or 1. For some random dude, he won't be able to distinguish between. He won't be able to tell whether it's a 0 or a 1. And so if you can do that, you can basically build all kind of encryption, because now you have you can encrypt anything because everything is binary. So E will send out B transpose equal to S transpose A plus E transpose. This is your public key. And so okay, so this is done. So now here this guy is sampling a random vector X, a binary vector with n and m entries. So in cryptography, you randomize things. The reason why you randomize is there are some assumptions, but basically what happens in cryptography is that you want that if you have a particular message and you're encrypting it, you do not want two encryptions of the same message to be the same. There are reasons for that. Basically, you can break encryption if that happens, if that's deterministic. So basically, encryption is a random function in cryptography. It's not strictly required, but a lot of security comes from the fact that some random. So let's say you're sending some message, let's say some critical message a lot of times. So a random person would be able to see the same encrypted text, and he's like, oh, so he's leaking some kind of information, right? You're leaking the fact that you're sending the same message repeatedly. And in fact, modern cryptography is so strong that even that any kind of information the eavesdropper won't be able to know, assuming that he does not have the power. So okay, so let's talk about one thing. I just want to tell you. Let's say the eavesdropper, the person who's looking into your messages, has infinite computational power. In that case, is encryption still valid? Any ideas?
Could you define infinite computational power?
Let's say he can solve exponential. So he can do something like O of 2 to the power n, let's say n time or something.
Okay, he can do O 2 power n in n times.
I mean, he can do it in feasible time, let's say.
Feasible time.
As in something that will not take the entire time duration of the universe to, You can just brute force, right? You can just brute force over your.
Yeah, I know brute force can work, but yeah, all right. I mean, it technically should be that, because I mean, one can at least do RSA by brute force technically in those terms. What about lattice? No, okay.
No, I'm just talking in general. RSA by brute force, right? So again, that is only possible under, let's say, when E is 3 and you know something else. But in general, RSA is not breakable, right? Because you would require 2 to the power 128 or something. Right?
Yeah.
Right.
But
again, yeah. So basically, the assumption in all of this is that your eavesdropper has finite computational power. So he's not some super god. He's not a super power. So in the assumption that he is limited like us, in a sense, that he cannot do 2 to the power 120 computations. And in fact, there's a very stricter definition to it. It's called there's an assumption to it where I forgot the name. Negligible. So he can only do. Let's leave it for now. Okay. Basically, the idea is that you are assuming that the eavesdropper is not able to just brute force the sex. Right. So that's the assumption here, and that's why you're adding a randomness. So Amy, Alex will send this vector BT go to STA plus ET, and so now for my guy here, for him this B, he knows it's of this form, but the entries of it, I mean, he's not able to extract the S out of it. For him, it might as well be a random vector. Okay. So now what Bob is going to do is he's going to create he's going to multiply A with X, and A is known to everybody, and send it back. Okay. So this is called a ciphertext preamble. And this is required for the decryption part, right? Yeah. So now Alice gets U, she gets it, and then he sends U dash equal to B transpose X plus a bit into Q by 2. What is Q? Q is the size of the group, size of the field. So in this case, it could be 2 to the power, so a very large number. Okay. So now let's look at this. So this value, Alice receives, and let's do this computation. Let's do, so Alice knows S, right? And S is also randomly generated, by the way. So this symbol means you take random elements from the set. Okay. So U dash minus S transpose T into U, what will it be? So when you do S transpose T into U, this will become minus S transpose T into AX, right? Minus S transpose T into AX, which, if you think about it, is nothing but B transpose TX minus E transpose TX, right? So this will get cancelled, and it will be left with bit into Q by 2 plus some term E transpose T into something. And the assumption, because remember, X is a short vector, so E transpose T into X. This will be bit into Q by 2 plus E transpose T into X. Now the assumption here is that X is short, because again, it's from 0 to 1, E is short. So this will be a very small element, right? So this, you can neglect it. So you have bit into Q by 2. So if the bit is 1, this is going to be a very enormous number. If the bit is 0, it's going to be a very small number. So you can extract the bit with very high. In fact, this may seem probabilistic. The thing is that the size of Q is very, very large. So it's very insignificant that you make a wrong prediction, given the fact that you know S. Okay. So this is how you decrypt. Now let's talk about the security. I think I have, yeah. Right. Okay. So now, so again, so why is it secure? So this guy, he sees A, he sees B, he says U, he says U dash, right? And for him, this B is indistinguishable from a random vector, right? That's the assumption of LWE. So now when he sees U dash, he basically sees some random vector added to some element. Now for him, the random vector could be anything, right? It could be very large, it could be very small. So you have basically masked this, right? So this U dash will also be random for him, because you're adding a random element to some fixed value. So this can be either 0 or Q by 2. So you can prove it that if you add a random element to some fixed value, the distribution of this, at least for this guy, is going to be random. So whatever he sees, it's indistinguishable if you just give him some random stuff. You give him random U, you give him random B. That's the same as doing this entire deterministic computation, not deterministic, doing this encryption. For him, seeing a random entry and seeing these encrypted texts is the same. So because it's random to him, the bit could be either 0 or 1. So you have encryption. And that is, again, this is very hand wavy. You can have proofs for this. The proofs get very mathematically demanding, by the way. So yeah, so that is the gist of how you can build public key encryption. So the idea is, she gives out a public key, this guy encrypts and sends back stuff, and she can decrypt it with a private key, which is S. He gets back bit into Q by 2. So, and you can do this for every bit 111, and you get back your message. Just one note I want to add: if you ever plan on studying theoretical cryptography is not very practical. Like whatever you do here, like this may seem very, very contrived. You did so much for a single bit. Imagine sending a 4 GB file using this, right? This is going to be really, really bad. In fact, a lot of theoretical proofs do not really consider practical things. So even though we have such mathematically defined hash functions and mathematically defined primitives, we still rely on very heuristic computation. So if you've heard of AES or DES, these are functions that are based upon random assumptions. They have random constants flying everywhere, and the idea is that it's difficult to invert. There's no mathematical proof. In the sense, even in cryptography, in the cryptography, at least we have an axiomatic principle that some functions are hard, some computational problems are hard to solve, and from that we build everything mathematically structured, right? But in heuristic, in practical cybersecurity, even that is not there. They just do random stuff everywhere. So that is where some people would disagree between theoretical cryptographers and the practical people who you would call the ethical hackers out there. So yeah, that's one thing. And yeah, so you have built public key encryption. So that's basically it. So using this, again, assuming that LWE is hard, you have public key encryption. And so you basically have both the cornerstones of cryptography, public key encryption and secret key encryption. There are other things out there called signatures, digital signatures, and medium access codes that you can build from these things called GGH and NDRU. I'm skipping that for now. We don't have much time. So, but yeah, that's mostly the rough idea. I hope you got some intuition about what cryptography is, how lattice can be used for things, and I'll share the resources with you. So if you want to really study cryptography, I would say this course is really, really very nice. So this course, this is CS406, and it starts from the ground up, and you get the complete mathematical flavor of cryptography. So fun note, some friends of mine took this course thinking that it's going to teach them how to hack into people's accounts. They had a very big reality check. I think 60 people had signed up for it initially. It dropped to 20 because this course is like a very mathematical course, and it's all about proving things and figuring out theoretically what things are. So I recommend you take this course if you're interested in cryptography. I'll share you some resources along with this PPT, and if you want to know more about lattices, I'll also share the resources I use for studying. I guess that should be it from my end. Do you have any questions as such in general regarding anything about cryptography? Or I'll confess I'm not a very big expert in lattices. I just studied it for some time. So, but yeah, I hope you had got some idea, and I know you were expecting something else, but yeah, this is the best I could do. Yeah. So, any questions or anything? Any comments?
So hi. So thank you so much, Pradipta. It was so last minute. I mean, we really were in a sticky situation. So thank you for coming along and giving this wonderful talk. I'm sure we all, I mean, at least I learned a lot about cryptography today, and I think it is one of the things I am actually genuinely interested in. So yeah, I mean, thank you for coming along. This was great. I hope you all had fun. You all enjoyed. Again, I mean, I can't express my gratitude for you, Pradipta. It was great. Thanks a lot from the entire MNP team.
Thanks a lot, guys. Yeah, great to be of help. In fact, I'll share those resources with you. I mean, you can do a post somewhere, I guess. I don't know. Do you guys do a how would you? I mean, there are 20 people here, I guess, so they would be interested. I'll share it with you. I'll share it with Rohini, and then you can basically,
Yeah, sure.
if you want to have further interest in this thing. Okay. So okay, I'll be taking your leave then if you don't have any further questions.
Yes, thanks a lot.